it's about understanding what this chapter is about, or what should we know after we learned or discussed this chapter. So this is about what the tidy model packages are about. So like a motivation to why learn these packages. We have quite a few definitions around models. What are their goals, and how can we classify these models? I guess these are not R or tidy model specific, so these are like general modeling terms. And how modeling, and we will see how modeling fits into the broader data science workflow, what steps are there. Yeah, so these are two quotes. Yeah, so modeling is about like finding relationships, and it is usually useful if it introduces some kind of simplicity. So this reductive for me, it means that the model is simpler than the data. So the model is always simpler than the actual reality, but we can use it somehow. And yeah, the other one is, it's good to learn modeling. It's good to have better tools for modeling, because there are more and more models every day in more and more areas of our life. I guess it's, we can see it that what I really like is this idea of bit of success, which is not just about tidy models, but the tidyverse in general. So the idea is that these packages should make modeling easier, and it should be, and it should, so it's not necessarily means that it's easy, because modeling is a complicated process. You have to pay attention to a lot of stuff, but it means that it should be easier to use it correctly than to use it incorrectly. So it should be generally a good experience, and if you use it more, then you should be better at it, and things like that. So two related thing is that it should be easier to use properly than to use it incorrectly. So, and yeah, I guess it's two quite closely related things, so that you don't make mistakes. And maybe confusion is not just about making mistakes, but about how easy it is to find what function to use, or how easy it is to know which argument means what, and stuff like that. So I think some examples that help this. One is internal consistency. So if you learn, maybe you learn about how to specify the number of trees for some specific tree-based model, then if it's the same name for another tree-based model, then you can apply the same knowledge that you learned. So it's easier to learn. Another thing that helps with this is to have good default values. So like I think Daniel mentioned that if you want to show that for someone new to R that how easy it is to do modeling in it, you will probably just start with a single line of a linear model fit. And for this, like maybe if you do a model, then you can have like really few lines of code and have a meaningful model, and then you can refine it later. And that way it helps you to start. The third one, which I think is really important, is to have good error messages. And I guess like with Bayes-R traditionally, there's a lot of cases where a piece of code won't fail, but rather maybe just produce null or produce a result. So it will try to work, but somehow it is better to produce an error message if something's unclear or if there's missing data or something like that. So maybe at first sight errors mean that it's not that easy to use, but I think it's in the long run it's better to know your errors than don't know about it. Yeah, I guess this is kind of a meta stuff. So the second chapter, or the second idea that is in the first chapter is what kind of models are there. So there are 3 models differentiated. The first one is called descriptive models. So it's like to show something, but maybe it's just to inform you, and not like with a scientific precision or things like that. So it might give you an idea of what to do. I think the 2 more well-known examples are inferential models. Then you have a hypothesis and you want to know whether it's true or false, usually, or how true it is. I guess the most taught example is clinical trials, where you have a treatment and you want to know whether it's better in so it's better than no treatment at all. Yeah, so the output of this inferential models is like a statement that yes, these groups are different, or yes, this treatment has an effect. And usually, of course, it's as with some kind of probabilistic output. And usually with this kind of models, it's also noted that you don't know whether you are right. So by the very nature of the p-value, for example, you don't know whether your conclusion is correct or not. Maybe if you later, maybe you repeat the same experiment with a larger sample size, then you have so you can be more confident, but it's not proof, just probability. Yeah, and the third category is predictive models. So it's about So usually you build a model on some data, and then you can apply it on new data and have some predictions. It's not necessarily about the future, but it can be about the future. So examples are predicting the weather, or the revenue of a company, or maybe the blood pressure of a patient, or things like that. There are subcategories. I guess it's mainly related to what method you use to build these models. So mechanistic models are when you have some kind of proven relationship between different data points. So there are, I think one of the examples is measuring how much insulin is in someone's blood, and then it's useful because there are things that are easier to measure and things that are harder to measure, and maybe if you measure some things easily and then you can calculate the desired value, then it's useful, and you can define this equation by which you come by the prediction. I guess I'm not sure about good examples for this type of model. But usually the truth can be acquired in some way. So maybe there's some other method to measure the same thing that you predicted or calculated, and then you can know how accurate is your model. And there are so-called empirically driven models. Where you don't really know why your method is working, but it's working to some degree, and then you are happy with it. So, for example, if you are, let's say, predicting stock prices, you know that the financial market is a really complicated thing, and you don't need to prove why your predictions are working, but if they are producing money, then you can be happy about that. So, or maybe you see that maybe I don't know, some kind of animals behave similarly if they are geographically close to each other, and then maybe you are happy that you can use that information, and then you don't need to prove it, or it might be useful somewhere else. Yeah, I guess when I read this, I was thinking about that maybe there are some other models. So for example, sometimes there are news about what some neural network type model maybe generated an article, or they try to write movie scripts with AI and stuff like that, and then it's I guess it's not really predictive or inferential or descriptive, but it's still some kind of model in the sense that you pour in a lot of data and you get out a new thing, and maybe you can measure how good is the script by, I don't know, seeing how many people like the movie or how many people thought it was written by a human and not by a machine. But maybe it's, so I guess it's in the general language, these are also models, but maybe not in the same sense that we can use these packages for. So it's just, I was thinking about this. Yes, so these are more general model-related definitions. So we speak about unsupervised models when there's not an outcome variable, but rather we see some relationship, for example, principal component analysis for dimensionality reduction, and clustering, or autoencoders. I guess they are type of neural network also for some kind of dimension reduction, although not in the same sense. So you can. So my first idea was that you don't really know whether you succeeded or not. So you can't say that this model is more closer to the truth, but you can still say that. So you can still define measures, for example, for clustering that how good they are. So you can still measure their usefulness, but it's not that you have like a single target variable that you want to predict. And second, so like the opposite is supervised models, where you have a target variable. Sorry. So I guess this will be discussed in the majority of the book. And we can further group these into regression and classification based on whether the target variable is a numeric. So for example, predicting sales or blood pressure, or classification, then maybe, sorry. So in classification, you want to predict or say that something has a label or not, or maybe there are multiple classes. So for example, maybe it's quite a lot of discussed example is to recognize handwritten digits for postal codes and stuff like that. And then there are like 10 well-defined classes that can be written on a postal envelope, and then you want to say that each digit or picture belongs to one of these classes. So that's an example of classification. You can have 2 or more classes. So these are the 2 main types of models from this perspective. And based on the data that you use, Usually the data is either quantitative or qualitative. So qualitative here means that it's not a number. So it's like when the target is classification, it's a few values, and when the data is used, it's qualitative. A lot of the times it's not clear at first sight. So maybe you have a data and it contains only zeros and ones. And at first sight, it may seem that okay, it's quantitative because they are numbers, but the 0 and 1 may encode some property. So maybe, I don't know, spam email may get ones and non-spam emails may get zeros. Yeah, thank you, Daniel, for. I guess a lot of models, if you have a factor variable, then you have to convert it to numerics so that the models can eat it. But still, the data in its nature, it's not numerical data. So it does not make sense that it's 1 more or 10 times more or things like that. Also, the data can have different roles. The two most important roles are outcomes, so what you want to predict usually. And so this makes sense for the supervised models. And usually there is one outcome variable, and all or most of the rest of the data are the predictors. For example, you can try to predict the number of accidents at a traffic crossing based on the day, the weather, how many cars pass there, whether there's a traffic lamp or not. And so you can have a lot of different variables used as predictors. And also there can have like maybe a unique identifier or something that does not make sense from the modeling perspective, but still important for the data to be able to maybe connect to another data set or something like that. I guess so sometimes one of the most difficult things or the most intimidating is how to choose a model, and it will usually depend on what questions you want to answer. Also, what data is available to you. Yeah. Yeah, so I guess many of you said that you are already familiar with the tidyverse. So this is an overview of a general data analysis process. So usually you have some data available in some format, then with importing you bring it in R, then you need to tidied, maybe there are numbers encoded as strings or missing values, or that there can be many, or there can be wrong records, a lot of things. Then you will transform it to suit your needs and visualize and model, and this is all about understanding your data better, and in the end, hopefully, you have some kind of conclusion that you will communicate to others. So, well, I think I skip this, or I guess it's, maybe we can come back later. It's not really modeling specific, just to see that modeling fits into the understanding of the data that you have. So this is a chart from the book about the modeling process. And so previously we had like a small box for modeling, and then now it's expanded to this quite big chart. So you need to have some basic understanding about your data in order to know if you even have the data to do some modeling, or if you have even the chance to answer your question with the data. And then feature engineering basically means for me is to maybe transform your data, creating new variables. So one example is if you have maybe data with the time, then it might make sense to use that time as weekdays versus weekends for modeling. So maybe the time has too many different values, or a lot of different values, and maybe, for example, for the traffic example, it's important whether you have weekends or weekdays, but it's not important whether it's April 1st or April 8th, but it's important whether it's weekends. So feature engineering is this kind of transformation where you transform your data with the hopes that the models will like your data better that way. Then you may try many different models. Yeah, of course, before you start modeling, you should know what is the purpose of the modeling. So what question you want to answer, and you should know beforehand how will you evaluate your model. So this can include, for example, what is a good enough performance, or what types of errors are acceptable. So, for example, maybe false negatives or false positives are more important for your use case, and you can weight your performance metric based on that. So you should define these questions before you start modeling. So these are like the non-technical part of this process. And then you can have a lot of different models. And this part is like a cycle again, I guess. So we can have like a big cycle of creating models, evaluating, then maybe transforming your data again, finding new variables or ignoring variables that are not helping the model. And in the end, usually you have the model that you see as the best. You can evaluate the model to see its performance and maybe see, so to see its performance, and then you have a model that you can use for several purposes. So maybe you just publish a research paper about it, or you use it to do some predictions, and so this is the summary of the first chapter, and let's have some questions, discussions. So was there something that surprised you, or that maybe you don't agree with, or maybe you missed something?
Not really. I was really confused about the mechanical models versus the inferential, but Daniel and Chris cleared it up in the chat. So.
Yeah, I couldn't follow the chat while presenting, but I will read later probably. Yeah,
is it just the nature of the problem, or like the algorithms you use to model when you define a model?
I think a mechanistic model is like based on physics, usually, or like a known evolution equation.
Yeah, I think the answer to your question is, I think it is the nature of the problem, because I'm like trying to think of examples, and it's like, well, I think if you just make the variable a different thing, it seems like that'll make it more mechanistic or not.
Yeah, I would say it's more on like flexibility, kind of. So like a mechanistic model has a lot of assumptions. So in general, it's more like inflexible to learn trends in your data. Where if you go on like the other end, like say like a neural network or something, is like there's no assumptions you give it about the relationship between inputs and outputs besides, okay, maybe you have a classification versus regression problem, but otherwise it's highly flexible and can learn those patterns itself.
Yeah, I guess I was thinking the mechanistic things as being, I don't know if it's right, but as being basically derived from a theory of how the world is, rather than the empirical ones are derived from the data that you have about how the world is.
Yeah, exactly.
So does that mean that for a mechanistic model, you don't even have parameters, or?
You have parameters, but I don't even think you necessarily need data. Usually you can like give it inputs and then see what the output is. And then you can use data, I think, to try to estimate parameters, but I think of it more as like a simulation thing.
Yeah, I think it's interesting because it might, like, I can think of like examples of mechanistic models where you would have data, but maybe it was from the literature, it was just like a summary finding of, I guess, the examples I think of, because that's what I worked on previously was in chemistry, but some data might feed into it, the model, about the rate of a specific equation, but it's less that you've gathered a set of data specifically for the purposes of the study. But I'm probably overcomplicating things a bit. Not quite clear on it myself. I'll think about it a bit more.
I mean, Chris mentioned like systems of differential equations, like I guess in epidemiology when we have those SIR models. It's mechanistic in that sense, but it's also like you use real world data to calibrate it, which could be like a stats model to calibrate. So it's sort of, yeah.
That's why I'm getting confused too. Yeah.
So I also work like in reinforcement learning, and it's kind of like a mechanistic model assumes the rules of how the world works, and then you can tune it with data. Whereas like an empirical model, you learn from the data what the rules are for how the system is working. So I don't know if that makes it any clearer.
Yes, somehow, but I was thinking about that when you train a simple linear regression, you also have very strong assumptions. So your assumption is that there is a linear relationship and that the errors are random. Of course, your model works if they are not, but there are also strong assumptions, just maybe different kind of assumptions.
Mm-hmm.
Yeah, but I like your example that they are not like physical rules about or not scientific assumptions, just model assumptions. Okay, so one thing we should discuss is who will volunteer to present the next chapter next week. And also I think it might make sense to volunteer for further chapters as well. So you have more than 1 week to prepare. But it's of course not, you don't have to volunteer for 10 weeks ahead or something like that. So
there are GitHub repo set up for this book club?
Yes, so there's a GitHub repo, and in the README there's a place to sign up. But I guess if you don't want to, you can also just sign up in the Slack. But you can like use the GitHub edit feature to add your name, and it will create a pull request, and one of the someone who is responsible for the GitHub will probably merge your pull request within a day. So here's the official place for that, but we can, I guess, just use Slack if it's easier. But it would be great to if we can have a volunteer for the next week, chapter 2.
I can do it next week.
Great, thank you, Daniel.
I can do the third week.
Yeah, and there's sorry, just one more thing. If you are new to GitHub, then there's 2 short videos to how to contribute to this GitHub repo with your slides. So you don't have to know a lot about Git and GitHub to be and hopefully to be able to edit this book down, which we use to collect the so-called slides. So yeah, so this is a way, if you are not that familiar with GitHub. Yeah, and also feel free to provide feedback about what was good or not so good about the presentation, or how can we improve it later. Okay, so I guess if there's no more questions, then we spent exactly 1 hour with this book club. And thank you for coming, and I look forward to next week, and then we can discuss on Slack if there's any questions or additions.
Thanks,
everyone.